Right. Good morning, everyone. I was also told there are only going to be 7 people here, so. I'm from the magical world of Google, where resources are free, everything works, there are no problems. I wish. So I wanted to give a slightly different view on the world. We build fairly big systems. You may be aware of that. And we have big problems that go with those systems. I'm a site reliability manager. My particular focus is on making Google run from the inside, so looking after Googlers and allowing Googlers to work. And my particular focus at the moment is actually externalizing a lot of our internal IT so that we act like customers to ourselves. So I wanted to talk about some of the things that we've learned about building large systems. Puppet will come up, of course, as part of this. But some of these lessons are really valuable for people to learn. As was mentioned before, some people are used to small numbers of systems, hundreds of systems, thousands of systems. We're also used to those numbers and some bigger numbers. So, site reliability engineering at Google runs many, many services, both internal and external. And as I said, my particular focus is on internal systems. There are some important rules that apply at all times. And every time you break these rules, you're waiting for a disaster. It's going to come and bite you. So the same rules apply. Make the service scale. That doesn't mean allow it to double or triple. It's 10 or 100 times. Maybe next week. Make the deployment consistent. And I can't stress this enough. And this is where config management, good config management, Puppet rules, manifest, etc., are important. Making that deployment consistent means that you can go to any system and have the same behavior for any particular release of what you're doing. As soon as you have a machine that's different, you are going to have interesting failure cases. And you're going to have that oops moment. And that oops moment is one of those things we want to avoid. In order to engineer reliable systems, you need to understand all layers of the system. And this is actually probably the biggest failure that I see when people are building large systems. I'm an application developer. I know how my application works. I've released my application. Great. Now, what about the database layer underneath? What about the network layer underneath? What about the disk subsystem? Slow disks affect the performance of the machine, affect the performance of the database, affect the performance of the application. Everything goes bad. Suddenly, timeouts happen. Database retries happen. Things go bad. Unless you understand all of those layers, how the whole system goes together, you're never going to really understand this system. And importantly, you're not going to be able to react when one of those goes bad. So you need to understand from the top all the way to the bottom, because any portion of that can fail. And more importantly, at any size, any scale, will fail. It's not can. It's one of these laws of percentages, laws of averages. If you're expecting a failure every so often and you multiply it by thousands, then it happens today or tomorrow. Disks fail. Obviously, monitor everything. What do I mean by monitor everything? Well, it's nice to know that your web server's up. That's useful. Most people do that. But how many requests is it handling? Okay, a lot of people do that. How long is each request taking? How long is each request of each type taking? What's the effect on the database for each of those requests? Which ones of these are cached? Which ones of these are expensive? Which ones of these cause a cross-system call? When that network's slow, when that switch is busy, what does that mean for your application? What's it going to mean all the way up your stack? So monitor everything. And this is a cry out to the developer side of the DevOps community. Please put monitoring inflection points in every piece of code you write. Anytime you're doing something to data, track it. Put out a variable that we can look at. We as the sysadmins, SREs, whatever you are, the operations side, you want to see this request went into the database at this point and took so many milliseconds and then popped out at the other side. I want to know how many went in, how many came out, and how long they took. Because then I can get an idea of the performance trends of the machines. I can understand when I need to scale, when I need to add more machines, when we're actually going to hit a point that we can't scale anymore and we have to re-architect. And those points come. Plan for failure. This is actually a really fun part of my job. Making sure that things break and breaking them, right? We actually do this. We take systems and we pull plugs. We break databases. We pull disks out from underneath machines. What happens to the system? Do we degrade gracefully? Does it all fall over in a heap? The second is not optimal. It's not something we want to do. So practice it. Actually take your system apart and see what happens. See what each of those particular changes does to your system. Slow the database down. Put it on some slow disks and find out what it does to your application. Load the disk with some other random application, some cron job that's actually behind the scenes, nothing to do with your application. One that I remember was the man page finder that runs cron and just runs through and finds all the man pages. It's a really heavy disk user. Right? You can probably turn that off because you probably aren't running your man command on those application servers. But if it's still running, your database is probably performing badly when you're doing that man cat. So, how do we do this? We scale. We build for scale. We tier our systems. We build up at each of the tiers so that they have sufficient capacity to handle failure. So that's redundancy and capacity, and testing, and failing, all of those. So we never deploy a server. If anyone comes to me and says, I want to deploy this application, it's on this machine over here, that's not interesting. I'm not going to let that go out the door. Because that is not in any way a reliable system. And as my title says, I'm a site reliability manager. I can't let a system go out where if that disk goes, the application's down. So servers break, power fails. If that particular machine goes down, then clients and DNS need to be reconfigured to point over to the backup server, which means someone pages my team in the middle of the night saying, that machine's down, can you please repoint DNS at some other machine over there? I'm not interested in that. I'm not interested in being woken up for something that computers can do. We know how to fail over between systems, so of course, at a minimum, you need to have multiple systems that can handle this application. And you need some form of automatic failover between the systems. You could do that through, as some people do, DNS round robining, where you have multiple IP addresses for the same service. But clients tend not to behave very well when you've got DNS round robining. Some will stick on one particular server and not bother to reevaluate and go over to the other server. So it's not a very good method of doing it, and you tend to want to deploy behind load balancers. Obviously, at our scale, almost everything is behind some form of load balancer. And we rarely have two machines behind the load balancer. So we deploy clusters. We deploy clusters of servers. They have a consistent interface to the outside world, the client applications. They provide ports at well-known addresses. And the clusters are available via DNS, of course. But clusters aren't good enough. Networks break. Servers break. Power fails. Someone's working in the rack and breaks the network connection and the whole cluster or the whole rack goes down. These things happen. Obviously, if possible, you're not actually serving in that cluster at the time, but things happen. Earthquakes, floods, and so on. Whole data centers might go out. A single cluster isn't good enough because that might be unavailable. So we always deploy redundant clusters. And we do, as best as we can, send clients to the nearest serving cluster. And that's an interesting definition. What's nearest and what's serving? Serving is probably something that you can determine by health checks from some sort of client application that says, okay, is that server available? The load balancer can withdraw access to the back ends. But nearest is difficult. What is nearest? Okay, your nearest data center you might say is over there. But is your capacity actually in that data center? Well, the client probably doesn't know. Are they actually being routed to that data center? That's actually a harder thing to determine, and as an application deployment team, you can't necessarily determine that because there's lots of stuff outside your control. Hardware being rebuilt, networking changes, fiber cuts, whatever happens, you might not be able to get to that server. That cluster. So we deploy redundant clusters. Note the redundancy, every layer of the stack, we just keep talking about that. And one of the technologies that we use internally is Anycast. And when I gave a similar talk in Sydney, I asked how many people in the audience knew what Anycast was or who'd used it. Can I just have a show of hands here? An eighth? Less than an eighth? So there's a lot of people who don't know about Anycast. Google provides a public DNS service on 8888 and 8844, which are available for people to use as their public DNS resolvers. We deploy that through Anycast. Anycast is a portable IP address mechanism. The same IP address is injected into the route tables from any available cluster, any available serving infrastructure. So from Google for public DNS, we provide it at many endpoints, and we inject that route from many of those endpoints. So when you go and look up 8888, your query from Australia goes somewhere, but your query from the US might go somewhere completely different. And Anycast has some interesting abilities there, or capabilities there. Obviously, being able to send you to the nearest available cluster is really good, but the really nice thing, and I'll talk about this a little further, is that everything has to be identical. Because if it's not identical, if you get routed to the wrong cluster, you get the wrong answer. That's bad. And the nice thing about using Anycast and requiring you to use Anycast for your deployment is it's now a requirement of your application deployment that any cluster can answer questions for any user. And that's really beneficial. Once again, consistency at any point. And then as an operations team, you know that it's perfectly safe to turn that cluster off and send the traffic somewhere else. That should be a no-brainer. You could probably even automate it, depending on what your system is. Because you know that sending the traffic to the US or Europe is still going to give the same results. We use Anycast both externally and internally. So we use it for internal application deployment as well, which is really powerful. And as I said, that's my focus. However, though scaling is fun, client denial of service is not. Another shout out for the application side of the world, but we do this to ourselves as DevOps. Poorly written code on a small number of clients, yeah, it's annoying. It'd be nice to fix that sometime. But do it at a massive scale, large numbers of machines, you can destroy back-end infrastructure. You can give it so much traffic through your badly written query that you'll actually bring down clusters. And our job as site reliability is to make sure that that doesn't affect users. Right? We need to stop that sort of problem, causing problems for your serving infrastructure. So I've seen many, many cases of this in my life in various places of, oh, it's just a little hacky piece of code, it doesn't matter, it's just a shell script and we call it every so often. Now call it 100,000 times a day. Right? Call it 1 million times a day. Call it 10 million times a day and think of what the effect of that is. These things do matter. So please, write good code, stage your releases. And I can't stress this one enough. This is all part of professionalism of release management. You need to understand that every rollout has risk. You need to move fast, roll out as quickly as you possibly can, but know that that next release, though it was harmless, though it just changed the size of that text field, brought along a new C library that actually had some bizarre interaction with DNS, right? Just through the matter of recompiling it. And you didn't see that. Of course you didn't see that. It's not what you were testing. You were testing the application, and you were just fixing that widget. But somewhere underlying, something changed that you didn't care about and you shouldn't care about. But if you haven't given soak time to that application on test clusters, on what we call canary clusters, ones that can go wrong, then you're not doing the right thing for your customers. So work with the service owners. It's very much a cooperative relationship between the developers and the release engineers. It's the only way it works well. And one of our philosophies within SRE is embedding SREs with the development team. We don't believe in the throw it over the wall and let it run model. It doesn't work. It doesn't scale. because you have too many paths along the way to work out what went wrong. Whereas if you've got a close connection with the developers, you can actually deal with the problem, understand the changes in the system as things progress. So stage your rollouts. Allow soak time. It looked good on the test server. Great. Does it look good on an almost production release set with real traffic? And does it look good 3 days or a week later? What happens in that nightly run that you'd forgotten about where all these records get touched? Have you actually been through all of that production proving before the release goes out live? And when it goes wrong, and I mean when, do you have a rollback plan? How do you actually get out of this? Oops, that release was bad. So have a release plan, have a rollback plan, and please test it. I've seen many, many cases where people have written rollback plans and they haven't worked. In the heat of the moment, they haven't worked. Oops, I forgot that we had to back migrate a schema change in the database. That wasn't in the rollback plan. Or we can't roll back because we're actually too far down the path, we actually have to do a reinstall. Now that may be a valid rollback plan. Reinstall may be a valid rollback plan, but call it out and actually go through it. And I've seen cases where people have written rollback plans, they've tried them and they didn't work, and they had to actually push a dead package to stop the program running at all. And then they could roll forward to a new release. And from a service infrastructure provider, have denial of service limits for your services and test them. Make sure that it's possible for you to limit the amount of traffic heading to you. How do you deal with that? So I've talked a little bit about load balancing. Load balancing is actually something I find fun. I'm one of those weird people. I suppose, as again, we are a room full of weird people, but this is our job. This is what we do. We'd like to be good at it. So do you have enough capacity to handle the load? How many backends do you need to serve the traffic? You actually need to do maths here. Or math, sorry. So you need to do the maths to work out how many backends are going to handle your typical load, how many are going to handle your peak load, how many are going to handle those loads a year from now, 2 years from now. 2 years is probably by the time you're going to have replaced the system entirely anyway. So you probably don't need to go to capacity planning much further out than that, but you need to have that 18 months, 2 year view of this system, and it's a rolling plan. So you've got this magic calculation. You said, we're fine, we can handle the peak load, and then half of your backends lose power. Right? The whole rack's just lost power. You've just lost half your backends. These things happen. And half of them are already out for repairs. So you're now down to a quarter of the capacity you had, or you thought you had. That's not fun. If they've all gone away, that's probably okay, because your load balancer is probably saying, well, I have no healthy backend, so I'll send them traffic somewhere else. But unless you've got appropriate limits and load balancing configuration, that quarter of your capacity is not going to be able to handle your traffic. And if it is going to be able to handle your peak traffic, you're probably over-provisioned. And back in this magical world of ponies, resources are free. I haven't found that to be the case. Resources cost. We have to build them. We have to deploy them. Everyone has those constraints. So you need to think about it. Be sensible. Make sure there's enough headroom, but don't go crazy. So how do you send clients to the right cluster? I've talked about this, but I would just want to give you a layer of things that you might think of in sort of progression of complexity and capability. Simple client configuration. So you can configure the client with multiple DNS addresses or host names that they're looking up. Kerberos is a good example of this. Kerberos, you can actually set multiple servers in your Kerberos config, and the Kerberos client will actually fail over happily across the servers. And that's really nice if the client handles the failover for you as one of the steps. But the client needs to be designed to do it. If the client's not designed to do it, you might get away with DNS round robin. DNS round robin just splays your traffic roughly equally across each of the available IP addresses. Then you could go a more complex idea, which is DNS views, where you give a different result to the client depending on who they are, where they're coming from. So you can do something different for Australian queries from American queries. Obviously, you now have complexity of working out whose traffic should go where and what do we do with New Zealand. Are they the same as Australia or not? And for the New Zealanders, they're not. Then one of my favourites is Anycast, portable IP address within your address space, either the global internet or your internal address space. And that's routed to the nearest, and I use nearest in quotes because there's fun about nearest, and I'll talk about that in a moment. And then one of the ones that I like is DNS views plus Anycast. So I actually put a DNS view in which says all of my traffic goes to that Anycast address. But I can put a view in that says, however, at the moment I need all the traffic for Australia to go over there. Right? So it gives you a coarse-grained traffic control that you can inject and move things around. Even if all the time you normally just send every traffic to the Anycast address, you can inject a route easily. Well, not a route, a different IP address. So load balancing is fun, but global outages are not. Monitor everything. With load balancers, health checks are there to check whether your backends are healthy. And if your health checks fail, by design, your backends go down, your servers go down. So if you get your health checks wrong, or you have some bizarre configuration or issue like I have seen where the date stamp handling of awk changed between Dapper and Lucid in Debian, that then caused time zone calculations for daylight saving to be wrong for an hour. That can be ugly. Test everything. Been here before. You should expect and test. Don't just write it on paper. Do it. Go through the procedure. Do it again and again. And once you've been through it many times, get someone else to do it. Try to pass that around the group. Get different people to test the rollback. Make sure it works. Expect and test the outages. A global outage can ruin your day. It can certainly ruin my day. Cascading failures where one of the clusters goes down due to load and it moves across to another cluster, which then goes down under load, which moves across to another cluster, which then goes down to under load, is extremely unpleasant. Things break. Learn from them. Get into a post-mortem culture. Right? We have a lot to learn from the medical community who go through post-mortems, understanding what went wrong. Focus on the facts. What went wrong? What could be better next time? And I stress this, and I hear people say, oh, postmortems are bad. I get in trouble for writing postmortems or being the subject of a postmortem. A postmortem is not about blame. It's about learning what went wrong. So other things that aren't fun, thundering herds. This is where I get into numbers. So for Puppet within Google, we have lots of Mac desktops and laptops. We have lots of Ubuntu desktops and laptops and servers, and we have some other things. All of those are largish numbers. So what if they all want to do a Puppet run? Yeah, nightly Puppet runs, that's fine. What about every hour? What if someone says, no, this config has to be out every 5 minutes? That can really hurt. You have a lot of people hitting your back ends. Randomize your cron jobs. This is trivial. It bites all the time. People just go, oh, that's fine, that can run at 3 o'clock in the morning. Not when they're all doing it. Test it. Add some fuzz delay as your startup. And importantly, how can you shed load on the server end? You can't trust that your clients will do the right thing. So how can you actually shed load at the server end? Talked about Anycast. Anycast is great fun, but it's coarse-grained. It just basically says all of this traffic goes to the nearest. But you can't actually, if you've suddenly got a lot of traffic in that area, you can't split it easily without route injection fun. So nearest, as I said, is hard to define, and serving is also somewhat hard to define because it might be low on capacity. So networks break, physical, routing, configuration, load balancer bugs, all of these can cause Anycast routes to go somewhere different. And Anycast monitoring is hard because you actually need to monitor Anycast from the location of the user. It's no point monitoring it from the data center. It's healthy from there. But what's happening for the traffic from this particular office? That's actually a tricky problem. That's not fun. This happens. This happens when all but one cluster is unhealthy, or the network's broken in some way, which causes a route failure, and all the traffic heads to, one site. So all clients could be sent to the same cluster. Anycast doesn't give you any control there. Be ready for it. What will you do? Can a single cluster handle worldwide traffic? What do you do if you can't? How do you shed that load? You need a mitigation strategy, and it needs to be built in. When it happens is too late. So include load calculations early in the health checks. If your servers are too busy, don't let them fail because they're under load. Let them withdraw themselves because they're under load. Your health checks need to know the health of the machine in all sorts of places, including the load that they can actually handle. The health checks need to have capacity planning in them. As I mentioned, consider DNS views to send some of the traffic somewhere else. And it's not the worst thing in the world to drop traffic. Cascading failures are far worse, because now you're dropping traffic randomly everywhere, and lots of it. So drop traffic if you have to. And finally, a big plug for diversity for people. We've talked about this a lot at conferences recently. One of the things that's been mentioned about sysops, sysadmin, DevOps type world is that we're not very inclusive. That's got to stop. Right? Diversity is important for people, but it's horrible for platforms. Stop it. If you can't automate it, you shouldn't do it. If you had to go onto that machine and tweak this config file to make it a little bit different, you're doing it wrong. Because when someone says, oh, this is great, sales and marketing come to you and say, can we have another 50 of those up today, please? And now you've got to tweak 50 or 500 or 5,000 config files, you're going to get some of those wrong. And that's where you lead to, that backend was just a little different and oops, post-mortem time. And as I mentioned at the start, Anycast can help you be consistent. And the nice thing about it is that it requires you to think, can I handle any type of query? If I can't, I shouldn't be using Anycast. If I can't, have I got the right deployment model? And finally, we probably all know this from experience, but every OS upgrade is a time to refactor and clean. Get rid of cruft. It's amazing how long cruft lies around. Okay, questions? No questions? Oh, there's a microphone runner coming round. I think. Okay, do you want to yell? I'll try to repeat the question. The question was, when I was talking about DNS round robin, am I expecting the client to be smart enough to try others? That's very much client dependent. Some do, some don't. So obviously the client needs to be able to understand that there's multiple options here. SMTP clients are a good example of ones that typically will retry all of the available IP addresses, but the clients need to be able to handle it. Sorry? Oh, DNS SRE records. I've never had a need to use them, so I don't actually have an opinion. That's not a for or against, I just haven't had a reason to use them. Yep. I didn't catch the first part. Can Anycast be used for UDP as well as TCP? Yes, absolutely. It's just an IP address injection into the route table. Persistent connections? Yes. Okay, so the issue here is TCP of stateful connections. So if you've got a connection to an Anycast address serving in cluster A, and then the route flaps, that connection will break and connect to a new site. So yes, that is one of the downsides of Anycast. I saw a question over here. more explanation about how we use Canary Cluster. I'm almost out of time, so I'm going to take one more after this. We have a multiple level Canary system. So we obviously have dev and test and stage, which we expect the developers to go through. Then we tend to have clusters that we can send traffic at that we, as the operations people, can just beat up the application appropriately with a hands-off approach. And then we tend to turn some machines into Canary machines so that they're serving live traffic. But we know that those machines are ones we want to withdraw if something's wrong with them. So if they're not behaving exactly like the rest of the system, the rest of the cluster, we just pull them out of service. Then we might expand to a full cluster of canaries. So all the cluster is handling the latest release, and then we might roll out. And there's time for one more. Question is how to best round-robin data service such as database backends. Yeah. So database backends, that's typically local, but not necessarily. That tends to be not Anycast. It's just trickier because of things like persistent connections and things like that. So that tends to be load balancing, local load balancing, but not necessarily. It depends how persistent your database connections are and whether you can handle those in multiple places and the inter-transaction consistency that you have to worry about. So I don't think there's any good answer to that or complete answer to that. Okay, well, I'm out of time, so thank you very much for your time.